nanohub.org. Online simulation and more for nanotechnology.
So, my goal today is to discuss the statistical design of experiments. That will be the topic I'll be covering today. And to get started, I need to first tell you about the story so far. And the story is essentially, you may remember that what we want is we have some set of input variables, and then we want to calculate. And we also know what is a set of output variables. And in lecture 1 and 2, what we started with is that somebody has given us this output variables, y1, y2, y3, and so on and so forth. And these may be the breakdown time of a dielectric. Somebody has given it to us. And they have requested us, let's say, to analyze whether this distribution is variable distributed or whether it's a log normal distributed, and so on and so forth. And in the first lecture, in the first few lectures, we talked about how to sort of take the data, plot the data, get rid of the outliers, and so on and so forth. So that was our point in the beginning. We didn't really want to even discuss about this hypothesis, but rather we wanted to just focus it and clean it, plot it, look it in leaf and stem diagram, and so on and so forth. Then what we did for lecture 3 to 5 was to assume various types of functions. It can come from physics, it can come from previous experience, that it could be a variable distribution and all. But before we could fit the data, we had to find a procedure, and that was the maximum likelihood method, by which, given y and given an assumption about f, we found how to best get the parameters that would describe it. For example, alpha and beta. That would best describe it. Then, in the last 2 lectures, and also by the way, at the time we also discussed the goodness of fit, that if 2 models fit the data equally well, then the question is, how do you select which one is a good? AIC, the adjust residual, those were the things. And then we discussed 2 lectures on, if you know the input functions, then you can do the scaling of the input variables, and I explained to you what the procedure is in terms of that. And even if you don't know the functions, the Buckingham pi theorem and others allowed us to reduce the number of variables. So that is how the story so far in that sense. But what we want to do today is to explain that, previously somebody gave it to us, and we had no say about how the experiment was done. We were a passive analyst. Somebody gave it to us. We had no. It's like in the stock market. You are not the stockbroker. You are just stock analyst. So in that case, you have to do whatever we have. For example, let's say somebody wanted to explore what this function is, and that person only took the data of the first 3 points. If you start with that type of the data points where the data itself is not very well represented, you have not really thought about the function well. So in that case, of course, your fitting is not going to be very good. It's not possible. For example, if it's a log normal, you obviously want to sample things in the log in time, in the x-axis. And if you don't do that, no matter how much post-processing you do, statistics cannot recover the physics that has not been measured. So that is the whole point of today's lecture. Now, this is actually started with Fisher, and this whole thing is called design of experiments. And the design of experiment is a foundation of modern manufacturing. In fact, every company does design of experiment. For example, often Intel, when they want to design a microprocessor, they may run 400, of these wafers with slight variation of some has little bit more doping, some had little bit more processing temperature, and thereby they optimize it. But how do you sort of handle when you have about 1300 steps? How do you optimize such a gigantic optimization problem? With 400 wafers, you are lucky that you can do it at 400 wafers, and yet that's very expensive. So Fisher actually started it, and I think for many of you, you should read the life of Fisher in terms of seeing that many people often think that if you want to do good research, you have to be in the academia. Far from it. Often the best research is done in industry if you can find a beautiful problem to work on and you have the passion and originality to do it. So that's something. But the work was originally done, it's revolutionary. He is the sort of the father of modern statistics. And then Taguchi in 1950s actually formalized what he had in Fisher. Fisher was very intuitive, very highly creative. On the other hand, Taguchi was much more formal, and Toyota ascended to be the leading company in car making. Before that, Toyota was not even an important company by essentially using this type of Taguchi method. So that was how these things are very important. So modern, I'm saying what I'm telling you in this 1 or 2 lectures is the foundation of modern manufacturing. So as I explained to you before that before Fisher, the experimentalists did whatever they wanted to do. They had generated some data and they threw the data to the statisticians that now analyze this. And then the statisticians did the best they could. And Fisher's point was that if the statisticians are not involved from the very beginning, the statisticians cannot get more data. They are magicians, but they are not magicians of that sort where they can create things out of thin air. That's not possible. So that was a very simple observation, but of course, that observation by itself, many people can say that. But the thing is that then you have to give a recipe, that do it this way. Just saying that you should involve us in the beginning of experiment, that is not really good enough. So this is an example I show in my reliability course, taken from there. But you get the idea that this can be, of course, anything. So for example, let's say you have a drain current and you want to increase the drain current of a MOSFET. And so it's a performance metric, higher the drain current, faster the circuit. So you want to design a MOSFET that has higher drain current. Now this could be a car that goes fast, right? What is it, Alfa Romeo or this, whatever the fast cars are. So you can say this is the speed and this is that fancy car. And then of course you have a set of input, all of which in some way or other can affect your drain current. And here, for example, I've said oxide thickness, doping, anneal temperature, junction depth, and all these things that you can think about. And you may remember in the Buckingham pi theorem, we also assumed a bunch of things. If you have an equation, great equation for MOSFET, in that way it's fine. But often for the extremely short channel MOSFET, you have many interactions. So the long channel formula may not really work fully. That could be a starting point, at least to give you a list of variables. But you may need more or less. For example, halo implant is not something that you did see it in a long channel formula. And often if you can, you should combine them so that combine these variables. And that's why Dennard scaling rule is so powerful, because it allows you to connect the variables. So that can reduce the number of experiments, like the Buckingham pi. But let's say whatever you have, at the end of the day, you have a bunch of input that you have decided, and then you have decided to measure a certain output. It doesn't have to be one. It can be multiple objective output functions. Now, I have to define a few parameters before I go, because the language, different branch of statistics have different languages, and so therefore, let me explain it to you the way, in a very simple way. For example, what we call parameter often, they call it factor. Parameter means the variable that we are changing. So for example, oxide thickness could be a parameter or a factor, doping, channel tail length, this could be names. So whatever the variable names, those are called the factor. and whatever the specific value of that variable, that is called the level, right? You say, let's say water. So, how in a farmland, let's say the water is a variable, and then how much water farmland A has farm A has with respect to farm B, that is the level. So, that's level. So, here for example, you have 1 to 3 nanometer, you want to check which one gives you better performance. Doping is, let's say, you sort of know that you don't want to be at 10 to the power 15 or nor you don't want to be at 10 to the power 19 from empirical experience. So, you want to test 10 to the power 16 and 17, let's say. Channel length, you want to do it for a few different channel lengths. We already know the answer in some way that if the channel length is long, then the current may not be vary for a given voltage. We know. But, if you didn't know the physics of MOSFET, then you wouldn't know. So, that's why you want to do an experiment. And of course, in each one of these experiments, combination, you can take a combination of these parameters and you can essentially do it a few times. That's called a replicate. So, what you do, for example, one experiment could be 2 nanometer, 10 to the power 17, 4 micron, you put it in a wafer and then you run. And then you have other combinations. So, you can very quickly see this is a combinatorial problem, right? You will very quickly see a combinatorial problem. And combinatorial problem, as you well know, very quickly explodes. The number of combinations that you have to test very quickly explodes. So, you can immediately see, yes, it was good to bring the statisticians in, but the thing that they said is going to cause us big trouble. So, statisticians not only have to say how to design it, they also have to say the engineer has a short amount of time. So, within that time, whatever experiment I can do, what is the best experiment? That is the challenge. If all combination could be tested, then we don't need a statistician. We could just do it ourselves. So, this is a language that we will remember and then we will use at various times. So, the first thing example, so what I'm going to do is to give you some examples that you sort of know about to illustrate the principles first. The first principle is the experiments has to be randomized. What does that mean? By randomized, I mean that, for example, let's take this example. Let's say I have, this is from Fisher, so therefore I'm using the very similar type of thing. A, B, C and D, let's say land type is farmland. So, some lands have a lot of, the soil may have sand in there, some may be very dry, some so on and so forth. You get the idea. And then 4 companies, you get the fertilizers from 4 companies and you want to know which combination, what type of land and what type of fertilizer. It's a, let's say, research lab for agriculture. It gives you the maximum output and then you would suggest the farmers that use that type of land with that type of fertilizer, you are going to get a good yield. So, that's like a drain current for the farmers. Now, the thing is that this problem turns out, this randomization problem, so they, this is how, think about it as a physical space. And then there's 16 parcels of land, and you can immediately see that these are constructed in a very special way. A, B, C and D, these are land type. And fertilizer A, fertilizer B, C and D is the fertilizer type. But do you see in the next one, you don't start with, if I were naive, what I would have done, I would also have done A, B, C, D here, and then I would put B here, and I would put C here, and then I would put, and then I would, that is, that I will just replicate this column here, and then I could get 16 combinations. There's no problem. 16 experiments I need, because 4 is 4 by 4, 2 levels, and 2 factors, right? 2 factors, land and fertilizer, and 4 levels. And so, therefore, I have 16. So, no matter how I do it, it is going to be 16. But the point is that I have to make it randomized. And the way it's randomized using this very special thing called Greco-Latin squares. Why is it? Where does the name come from? Well, because they generally, the first factor generally is a Latin word. And when Euler first wrote the equations, in fact, it dates back to Euler. Fisher copied it. These are written as alpha, beta, gamma and delta. And so therefore, those are Greek letters. So that's where this thing come from. And Euler was not thinking about farmland. I mean, Euler was a sort of in France at that time. He was not thinking about farmland, the aristocrats and all. He was thinking about playing cards. And how many, there are 4 types of cards and color. And how can you have a random combination of colors? And it turns out that this random combination, there are about 140 different, which are random. All of them are random, but you can choose any of them. And the point is the following. Why do you want random? Because, there may be a gentle slope in this four things, or one may be close to the other. So there may be interactions between them. And you want to design the farm in a way so that all the random variables, apart from the fertilizer, there may be sunshine or shading and all sorts of things, extra variables that you want to average the other variables out. That is the principle, that you want to all other variables should go away and only the main variables should stay. For example, the 400 wafers I talked about in Intel, if you have one set of experiment only doing based on one set of machines, now maybe the operator in that machine has not adjusted it properly. So the results that are coming out have a bias simply because you ran a set of experiments with this. But if you randomized it completely, then you can see the machine to machine variation that would have averaged out when you are doing the final result. The other one is, so this is, you see, this is already trouble because I have 2 levels and only 4 of this. And then I already have 16 experiments, and you can immediately see that if you have more, let's say you have, remember how many I had in the doping case. I had a transistor case. I may have 9 or 10 variables, and each one of them may be 2-3 different levels. Very soon, you will be in humongous pain. So in that case, what you want to do is you want to say that which ones should I do at the minimum that will still give me the 0th order estimate. So one thing is that if you can assume something about this, you can do this, reduce this. This is called full factorial. If you do the whole experiment, that's called full factorial. If you can do full factorial, do it, no problem. Most probably you will not be able to keep your job because your products will not be ready in time for market. So therefore, you cannot really do it. What has to happen is that somehow you must be able to take a subset, and that you can do if you know something about the function. If you can know something, then you can sample a little bit more efficiently. So this is something we know, like you may have played Sudoku. Sudoku essentially gives you in each square. What is the rule? The rule is that it has to be every letter has to be once at least, right? 1 through 9, and it has to be, and every column has to have that, and every row has to have the same thing, right? It's only once. And you know that this numbers given, which is already a fractional information, is actually the same as the full information. This too doesn't have any other information. This plus a rule is equal to that. And so therefore, you don't really need to carry, if you want to send your friend in the Mars any information about what this is, send the rule and send this measurements, the person will be able to recreate the whole thing. But of course, the rule doesn't exist. Rule is your assumption, and you have to check that whether your assumption is correct properly. But if the assumption is correct, enormous compression of the number of experiments you do, right? So I want to tell you how people used to do it before, and then a little bit of this. It will be a few details, but what I have already told you, that is the essence. That how to randomize the experiment. First, you have to pick the subset of experiments, and then you have to randomize them. These are the 2 principles, yes.
So I'm talking about doing the experiment or getting the results from?
These are the experiments. We are just doing which experiment we'll do. Which combination of the parameters should we choose before we doing the experiment. The experiment will give me the result, and I will analyze the result a little bit later. So, in old days, they said that, okay, let's say I have 9 variables, oxide thickness, doping, this and that, halo implant and that, and all, let's say 7. Yeah, I have 7 of them. And let us say that I am just thinking about 2 levels. Large oxide thickness 2 nanometer and little oxide thickness, thin oxide thickness 1 nanometer. Let me just for the sake of argument. So, what people used to do before Taguchi, with Taguchi and Fisher was to do this, and which probably we often still do. What they did was, let's say they will set this 1 means low level. It could be 1 nanometer, 10 to the power 16 doping. This could be whatever is the lower level, that's 1. And then we do that and we'll measure an output. This is the experiment has finished and we have measured an output, and output is 10 in some unit. It could be 10 bushels of corn, or it can be 10 milliamp of current and whatever. And then you change just one thing and redo the experiment. And by the way, you know how many you have to do in general. If you have 7 and if you have 2 levels, you have 2 to the power 7. You need 128 experiment. If you could do 128 experiment, no problem, you're done. But the thing is, we want to do fewer. And when people want to do fewer, this is how they used to do it. And so you change one value, oxide thickness 1 nanometer to 2 nanometer, and again do it. And you say, okay, 15 is the output. 15 is the output, so you like it because this has given you a better value. So then, never again you will shift from 2. So this column will forever be kept at 2 because it has given me better results. Then you change this at this one to 2. And when you change this one to 2, then you say that you get a 12. So therefore, that was not a good idea. You did something. You see, randomly, you have a humongous space, surface space. You are walking in the space to see how I can climb to the mountain. And anytime you have any local setback, you immediately throw it away. So then you get the idea that you keep doing this, keep doing this, keep doing this. And eventually, this once you like 2, you keep it 2. Once you say that 1, then you keep it 1 because the 2 did not give you good things. And so you reverted back to 1. You reverted back to 1 because these 2 gave even less results, and so on and so forth. And at the end of the day, when everything is said and done, you say that my trial number 6, this is the combination that will give me the best result. Right? This is the combination that will give me the best result. Now, you then specify the engineers, the processing engineers that go ahead and make with this combination. Now, you can immediately see that this may not be a good idea. This may not be a good idea. Why? The reason is that the actual 128 combinations are shown in this table. 128 combinations, for example, A1 is the lower level of A high is the higher level of A, and similarly B, so B1, B2, B1, B2. So you can see, you can take any column. For example, this column has A high, B low, and C low, for example, and then you can read from here. So because I have 7, so I have put 3 in here, and I have put 4 values in here. So A, B, C is in here, and D, E, F, G is in here. So at any point, I can write it as a code, which will, for example, this code is it will be 2, 1, 1, and then this is again 1, 1, and this is 2, and that's 2. So every one has a code. And so you can do the experiment. If you do 128 of these, that will be fine. But that's not how you did it. What you did was what I was doing I'm just showing you graphically what we did in the last one, which is non-optimum. What we did was that we did the first experiment where all the things were 1. These 3 were 1, these 4 were 1. So we did this experiment first, and we got an output of 10, right? So we got an output of 10. And then what did we do? We changed A, right? We changed A to, so we changed to high value. So this was our next experiment, right? everything to 1 except A has been changed to high. And we got a higher value. The second I got a higher value, I throw away the entire thing. Gone. Because I am never going to look for a peak over there again. This was what I did. And then I'll go quickly. Then the third experiment I did, R3, I got a 12. And the second I got 12 compared to 15, I throw away that. And then I did the other experiment. And then eventually I settled onto this one. So I throw away other things. So you can see this, if you could write a function in 3D, this would be a surface, 7-dimensional axis, and it will be a surface. And this is, we are saying that this is peak of the surface. Now this is not a good idea, because you see you are walking in a perpendicular direction. So this is how you go. You go from here to here, right? And then you go here in this direction. So let me show you. Oh, so this would be your optimum. This would be optimum, and then you should go ahead and do it. Very bad idea, because what it should be done is that you should not be doing the experiment sequentially like this, because if you change ABCD, just call BA and change the thing, you can come to a completely different answer. So this system is not randomized, and in randomized, if your experiment is not randomized, then your result cannot be, the thing cannot be optimized, right? And the simplest example is this. Let's say you have oxide thickness and channel doping, and you have somehow, let's say, your peak is, or valley is over there. You have, so let's say, minimum hot carrier degradation you want to do. So you are doing one factor at a time. So you are doing these experiments one at a time. And at this point, let's say you get some value, minimum value, 20, 15. So you'll probably get a 12 somewhere here. And then what you do, you go start walking on that and start going in here. And at the end of the day, as you start going in here, you may find that when you are walking this way, this point may be the minimum. Because as you start going here, it will be 12, 13, 15, because green is 15, 20. So somewhere here, maybe you find, so that's your optimum. But your optimum is nowhere near there. Your optimum is here. So therefore, this is a wrong way of doing it. So what you should be doing, so this is the problem. I mean, you can walk in this direction and then walk in this direction, never finding the optimum. That is the problem. So what do you have to do? So there are many methods. One is called this response function method, and the response function method, what it does, it says that, and I am going to show Taguchi one also a little later. What it says that you do 5 local experiments and look at the gradient. Instead of doing a lot of experiment like this, just locally probe which direction the water wants to roll. And you do that experiment, and then you start doing experiment, and then here you do 5 more. And just, 5 more here, 5 more here maybe. And then what you do, you walk. Again, you do the 5 more, and then this value will be lower than that value, right? Because water wants to go that way. So then you walk in that way. So this is what is it called? This is called gradient descent. Gradient descent. And this is an optimization technique we often use anytime we want to use machine learning or any other type of optimization problem. We often use gradient descent. Gradient descent just simply means this. Locally do the curvature. It's in 2D, do 5. If it's in 3D, take 9 points. And then simply walk in the direction that it's telling you to do. It will very quickly allow you to get to the final point. So this is also called orthogonal sampling, or response surface and orthogonal sampling. All right. So let me then continue on this discussion. I have to reduce, what is the goal? I have to reduce the number of experiments. That's my goal. I could reduce the experiment very quickly if the variables I have, they were completely independent, right? Let's say 3 of you want to do some work, and you divided it among yourselves and you essentially worked on your own, you can simply take it, add together and get the output result. That's if they are independent, if 3 of you are independent or 8 of you are independent. On the other hand, if being together either gives you more motivation to work or gives you more motivation to gossip, then the thing is that it's going to be a little bit more complicated, right? So the first thing is to focus on main effects. Main effects means individual effects. And somehow we start with individual effects, then we do pairwise effect, then we do 3 together effect, and so on and so forth. And that will work out. So let's say, I'm going to do an experiment backward. Let us say I know the answer, that student A, B, C and D, when they are lazy, they don't do any work, and when they are very active, oh no, I should not give that example because some of them are -6 when they are active. I do not know, that may not be a good answer, but you get the idea. So this is your 4 factors, right? This is 4 factors. This could be land, water, sunlight, and so on and so forth. You have 4 there, and then low sunlight and high sunlight, so on and so forth. These numbers are the output, the contribution to the final result is this at level 0 and level 1. So you can see that if only level, this is a full factorial. If only level 1 was here, then what do? You put just A. Others are not yet here, have not entered the room. So you have a 0 here, and anytime this A2, then you have all this 2. You just put all this 2. Why 2? Because that's 2. That's why you have given all of them to 2. When B entered the room, and when B entered, remember, they don't interact. You just sum. So then, can you help me out here? So what's going to happen? When B is in lower level, then these are all going to be 0. So I have added 0 here. And when B is in a high level, then I have to add it -6 and -6 here. So that gives me, when the A and B has entered the room, this is the interaction. And so therefore, that's the result. When the C has entered the room, I don't have to explain, right? That you get the idea that anytime, anywhere you see C2, you have to add a +4 over there. And when you have C1, all these rows, these 8 points, you add 0, because that was the value there. So I know the answer. So I'm constructing the thing, and then once you do D, you add the effect of D, and then this is the final result. If you did full factorial, this is the result you would have gotten. This is the result you have gotten, and your goal is really to go from here to here. This you didn't know. If you knew this, that this is the effect of doping, this is the effect of this and that, then you wouldn't have to do any experiment. This is what you have. And then you want to find this one. And it turns out that it's very easy. To go from here to here is actually very easy. How? All you have to do is to sum. So, for example, if you wanted to know the effect of A1, what you have to do is to sum all of them. How many do I have here? 8. What is the sum of this? Let's work out one so that we don't have to worry about it later on. Help me out. This is 4. 4, this is -4, this is 14, and 2, 16, right? So I have 16. And how many numbers I summed? 8. So if I divide by 2, then that would be -2. And then in the high level, in A2, I will just sum up these numbers and divide by 8. And that's the number. For example, so I'll put that number in at the level 2. And similarly, if you wanted to do D2, for example, D in level 2, what would you have done? You would have taken this row and that row and sum them up, divide by 8. And if you do that, you also get -2. It's just accidental that it's -2. It doesn't have to be. By the way, one thing did you notice? When I did this, when B was there, came in or not, C1 came in or not, D1, they were there or not, it has been randomized over all other people. And only thing that is constant in this column is A, what A did, and others have been randomized. And similarly, if you do it this way, then you can show that, for example, in here, you can see only D2 is as a level 2. Otherwise, A1, B1, A2, B2, everything has been randomized. So the effect of other people have been all averaged out. So this is the principle. And so if you do that, you will get, and then all you have to do is to subtract L2 minus L1, because these are all relative. These are all relative. If you subtract them, then you will get the effect of A is 2, effect of B is minus 6, effect of C is 4, and effect of D is 2. That is exactly what I started with. Do you understand this? I will have this as my experimental output. I will write a computer code to add things up, and then whatever result I get is really their individual contribution. Is it clear? Okay. And so therefore, when you want to do experiments, this principle of randomization is very important. This principle of how you randomize the experiment is very important, and that is what has to be done. So if, for example, you cannot do 128 full factorial, or in this case there were only 8, so therefore life was not that bad. But remember, I wanted, my problem was 128, and I can only do 8. Which 8 should I do? I should not really do it sequentially, one at a time, and look at the current. That's a bad idea. What I should do, I should randomize ahead of time, do the experiments, then wherever the chips lay, that's what it's going to be. So for example, I have 7 factors, and I'm saying that, let's say I will do 8 experiments. How do I know I have to do 8? Not 17, not 25. No, total is 128. So any smaller set I could do. How do I know? It turns out this Taguchi formulation gives you specific ones that says what is the minimum you can do. You can do more. But in this particular case, the minimum is 8. Now look at this. If you have done computer, architecture before, then it will become very clear to you. First one is like all ones. These are like 0, 0, 0, 0, 0, 0, right? 7, 0. Do you see in the next one what has happened? I have 1, 1, 1 and 2, 2, 2, 2. So I have taken all of them and simultaneously flipped all of them. And whereas I have 3 and I have kept them as 3. And similarly within that group I have kept it 1, and then I have kept this 2 at the high level, and then flipped this 4, and then 2 and 1. This recipe is given in a MATLAB code. If you say, what is it called? Fractional factorial. So, or you can just type Taguchi array. That will also give you. So this, what experiment you have to do, given 7 factors, is already given for you. You don't have to, you don't have to write this table. This table is given. You just look it up and then follow this experimental rule. So if you do that, what you will notice that no matter, this is completely balanced. If you look at the output, then for every time something, let's say this is 1. If you want to do what is the effect of A, then you can take all these variables and average them, because then in that case everything is flipping between 1 and 2. Everything is flipping because there is 2 B's, 2 1's, 2 C's, 2 C's, and so on and so forth, 2 D's, 1 and 2. Everything is sort of randomly flipping except A. And similarly in here, by construction, everything is flipping except A. And when you sum them up, any random effect of B will all go away. So this is the ideal experiment. This was a very simple insight that but what is the assumption here? Why can't you do it with so few a number? The assumption, the rule, so just like Sudoku rule. Here the rule is essentially you start by assuming the effects are independent. Now, it will also tell you that if it is not independent, it's going to tell you something. It will going to give you an indication that you are wrong. This is there is a interaction going on, so you better change your design and expand your design. But here you start. And since it is just a single level, so therefore independent, so therefore you start with this experiment. So this time actually you did an experiment where you did not go sequentially. If you just look at those eight things, like 1, 1, 1, 1, 1, 1, 1, which one is that? Better be this one. And then there was another one. This was that 1, 1, 1, and then this was 2, 2, 2, 2, 2, right? So do you see which one is R2? Right here. Right? So you are now sampling still you have 8 experiments, but you are now sampling the whole surface, but randomly. This is the point. And you are not waiting for the results to tell you which way to go. You are doing the experiments predetermined wise, and so that no matter where you are, if you just take all these values of, from here to here, all these values of A, actually you have 2, just 2 you have. But if you just do the sum and divide by 2, that will give you the effect of A1. I'm sorry, I should have said all of them. So take all these 4 values, divide by 4. That will give you the effect of A. Take all these values, divide by 4. That will give you the effect of B. And by doing it this way, you essentially are taking care of that if there is no correlation, then the effect of the other ones should all cancel out. This is the idea. And it turns out that if there is no correlation, by doing these few experiments is sufficient to get equivalent information of 128, because that's the Sudoku rule. Sudoku rule is that there is no correlation. That's the assumption. You don't know that yet. Now, what would have happened if the correlation, there was correlation? So, in that case, you see, let's say there is a correlation, that there are all these 4 rules when they are independent, but if B comes, if A comes in a room, then B doesn't behave normally. B used to, on its own, used to give a +6 output. Now, when the A is present at the high level, then B becomes -6, right? It used to do good work, and then as soon as the A came in, it's not doing any more work. It's going negative work, right? This is correlation now, pairwise correlation. So, I'll still be lower than 128, because 128 means that all 7 are correlated. 6 type correlation, 5 level correlation, all those. I'm just thinking pairwise, just for the time being. And then what you can do is that if it were uncorrelated, remember this table I just generated a few minutes ago, that had 0, -6, 2, and 4, just to remind you. Yeah, I'm just talking about this table. I just copied that table. I just copied the table. And then I copied the table. If it were uncorrelated, then this would have happened. But if it is correlated, then you have to see that anytime B is present, in that case, instead of adding +6, you have to subtract -6. So, I will ask you to check this one out when you go home. You can check this out, that this column is no longer this original column. The original column is 4, -6, 0, and -2. But remember that when A and B2 are present, then I have to really do -6. Sorry?
Minus, okay.
Yeah, I think this is +6. So, I should have probably redone this one. But they just I wanted to keep it this similar. But I'll fix it. But you get the idea that this value will be different. So, then what do you do? How do you know the value is slightly different? How do you know that there is a correlation? It turns out you can do this thing just as before. Remember that if there is a correlation, then this formula says AI and AJ, and you should do +- I plus j, you'd have to, this is a formula. If there is a correlation, then this value would be non-zero after you have done this. If there is no correlation, after you have done the sum, the value will be 0. So, that is how you know whether something is correlated or not. So, for example, if there's a pair correlation, by the way, A1, B1, this is Aij, so you have to do it, for example, by putting value of I and j and summing over all of them. A1, B1 is A correlated to B. A1, B1 is the entire green, because I would add all the C1, and then you have 4 minus 2 plus 2 divide by 4. You're absolutely right. That's my A1, B1 effect, irrespective of my CD effect. And similarly, I have A1, B2, which would be the sum of all this. And you can see 10, 14, 20, 28 divided by 4 gives me 7. And if I now put it in this formula, you will see that the value will be minus 12, telling me my original assumption about having this thing completely correlated, uncorrelated, was not correct. But this one is also telling me from this experiment that when I do the third order meaning A1, B1, C1, then I will just take these two values, A1, B1, C1. In that case, if I want to do third order, then the third order correlation, these are all pairwise correlation. So, there is no pairwise correlation, all of them are. But if I want to do third order, then I have to sum over I, j, k. And then that will tell me that whether, but so therefore, if this one is saying that there is no correlation other than AB correlation. So, what I have to do, what is telling me? That 8 experiment is not sufficient. I have to make the experiment a little bit more, because previously I had a little bit, anytime I have correlation, I have to do this. And then you can check for higher order correlation. We know by construction that there was no third order correlation. Remember, I just said when B is present, A does that. I did not say when A, B is present, then C does that. We didn't have things. So, by construction, the math will tell you that all the third order, fourth order, all these correlations would be equal to 0. So, therefore, you don't have to worry about them. Now, how do you fix for correlation? It turns out, because you want to know when they are present individually, what their effect is. And what you have to do in that case, you have to do what, if you are B alone, so B alone means this one and this one, B2 alone. And B1 is this one and that one, right? That gives you the total B1, 8 of them. So, you essentially take them and all the correlations, correlations with B. If you do that, remember there was 12. Do you remember that? This was 12. So, you are summing over them. All the B correlations, you are summing over them. And if you do that, you will get back that had it been alone, then it actually has plus 6. And once you know what its own contribution is, then you can find out what their mutual interaction is. And so, what you have to do, and this I will pick up in the next class, is that what you have to do, remember that I have A, B, C and D. So, generally I will show you soon that you have to have 4 columns in the experiment, Taguchi experiments, column A, column B. If you have A-B interactions, then you have to insert a dummy column, because you have to do more experiments now. That is called A-B. It's like a dummy variable. There's no A-B. It's either A or B. It's no A-B. And then you have to insert C, and then you have to insert the final column. I should have written 5. So if there is a column, then it expands to 5 columns, whereas previously, single, then it was 4 columns, right? So, in the next class, what I'll open, you can take a look, but I will show you how to choose the corresponding Taguchi array by essentially choosing from one of the tables. But the bottom line, I just want to conclude with the bottom line. The bottom line is, we cannot do all the experiment that we need to do. We have to do fewer. And the fewer, we cannot look at the results and decide which experiments to do. We have to do it statistical basis to take care of the fact that all the cross correlations are averages. Randomization is a key thing.